Okay, so on this question, they're saying use linear approximation, i.e. the tangent line, to approximate 1 over 0.202 as follows. Let the function be 1 over x, f of x, and find the equation of the tangent line to f of x at a nice point near 0.202. Then use this to approximate 1 over 0.202. Okay, so how do we do that? Well, let's start with the original function. F of x equals 1 over x. And I'm going to make that x to the minus 1 because I need to take the derivative. But I got to find the equation of the tangent line. So you know what that is about. Take the derivative. Down comes the minus 1. Subtract 1 from the power. So, and then we want that. Now it says at a nice point near 0.202. That's going to be 0.2. They just mean get rid of the stuff after the first decimal. Zero point 0.2 is going to be close to 0.202. So that's the nice point they want you to use. That's the x value. And oh, and by the way, let's find the y value that goes with that. How do we know what that is? Well, this right here is y, right? Because function values are y values. So y is 1 over x. So when you plug in the 0.2, you can hit the buttons on Desmos, it'll come out 5. Y is 5. I know that because 0.2 is 2/10 is 1/5. Flip it up, it's 5. So, okay, so that means we have the point 0.2 comma 5 for our x and our y. All right, so again, how do we figure that out? They said a nice point near 0.202. That means 0.2. So whatever they give you, just take the first decimal. That's something nice. It's nice in the sense it's clean. Doesn't have, it doesn't go on and on and on like 0.202 is just 0.2. And then plug that into the original function because function values are y values to find the y that goes with it. One over that's 5. So there's the x, y. Back to this now. So now we want to know f prime at 0.2. Plug in that 0.2. Okay, so if you hit the buttons on the calculator, you'll find that is negative 25. And that's going to be your slope, your m, um, on that. By the way, if you're interested, how do I know this? Because I know this is 1/5 because it's 2/10, right? 2/10 divided top and bottom by 2, it's 1/5. And then a negative power. So I don't know if you care about this, but I'm just looking at this thing going, that's 1/5 negative 2 power. Negative power does what? Flips things over, becomes 5 over 1 to the positive 2. So negative powers flip things. So that's negative 1, 5 squared. That's how I knew it was negative 25. Or you can just type it into Desmos. Negative 25. So we get the slope. Remember, so when we take the derivative and we plug in the x value, what we get is the slope. So that's the slope. So now we know the equation is y for the tangent line, mx plus b for the tangent line. Okay. So that's the tangent line. We know the m is negative 25. Can we know the x and the y up here? The y is 5. And the x is 0.2. And we have a b. So then we have, this will be minus 5 plus b. And 5 cancels. So b is 10. So the equation of the tangent line, x plus b. We already knew m was minus 25. And b is 10. So that's an important part of this process. We got the equation of the tangent line. That is the tangent line. Now, Remember what this is all about. This section is all about tangent lines are approximately the same as an original function where near the intersection point. Let me show you the graph now. Now that you've seen all this, here's a Desmos graph. Here's the original function y equals 1 over x. It's actually these two red parts are both together the graph of y equals 1 over x. I don't know if you remember from pre-calc, y equals 1 over x has two branches to it. The red. Now the blue is the tangent line right there, minus 25x plus 10. And see they intersect at the xy value right there. And you can see right around this area, the blue and the red are very, very close to each other. The blue is a good tangent line. And remember what a tangent line is? Tangent line is a line that barely nicks a curve in only one spot. And the slope of the tangent line is the same as the slope of the original red curve, the derivative, the slope, right at that one point. So the tangent line is a good approximation. It's almost the same. The red and the blue curves are almost the same when you're nearby their point of intersection. Now, if you get way over here, obviously the red and the blue are very different. Or if you get over here, the red and the blue are a little bit different. But right around where they intersect, in that whole vicinity, red and blue are really close. And that's why in higher math and science, physics, chemistry, engineering, they use tangent lines to approximate original curves. Why? Why don't they just use the original curve? Because original curves can be very difficult functions and they do high math stuff. Even for computers and stuff, it's hard to compute really difficult functions and do high level math stuff. So they like to use tangent lines because it's just a line equation. It's very easy to deal with a line equation for technology, especially deal with just a linear equation. It's just a straight line. The equation is just x to the first part. It's very simple. And they're almost the same when you're right around the intersection point, which happens a lot in chemistry, physics, engineering. You're just you're around that area. So anyway, that's why we do it. So back to the thing. Now, what do they want us to do? They said find the equation of the tangent line. We finally did that. There it is. At a nice point, x equals 0.2, just take the first decimal. Then use this to approximate 1 over 0.202. Okay, so final part. Now, approximate 1, 0.202, right? That's what they said. Yeah, well, how are we supposed to do that? Should we just type it into the calculator? No. That'd be the exact value. They want us to approximate. What's going to approximate? That means the tangent line. Remember, the tangent line is almost the same as this. This is the original function, 1 over x, right? Where they plugged in x is 0.202, right? That was our original function, 1 over x from the beginning. So they're just basically saying, hey, this is like 1 over x where x is 0.202. Well, they want us to now use the tangent line because that's going to be approximately the same in the neighborhood of zero point 0.2. So take that 0.202 and plug it in. It's going to be almost the same. It's going to be approximately equal. Hit the buttons on the calculator. I'm going to go to Desmos. Minus 25 times 0.202 plus 10. Minus 25 times 0.202 plus 10. Minus 25 times 0.202 plus 10. 4.95? 4.95, which hopefully that's what they got. Yeah, 4.95. So 4.95. By the way, remember, that's approximate, right? That's approximately the same as what? What was the original? Let's just do this just for fun. 1 over point. What is 1 over 0.202? Let's go back. Let's have Desmos do it. 1 over 0.202. See how close they are? 4.95 and then 0.49. So they're close. They're close. So that means, we can see that in the graph, right? Around zero point 0.2, around this neighborhood, the red and the blue are very close. We found the 4.95 is the approximate. That's the slope that's the height of the tangent line, right about here. And the other one, the red is just barely above it on that one. You can tell, if they ask you like which one's higher or whatever, you can see I'll do it here, the at point. So right here, we're going to have 0.202, what was it? Whoops, not that. 4.95. 4.95. That's the x and the y value for the approximation for the blue tangent line. Okay, but the red is going to be slightly above it at 0.202. The red, see how the red graph's just a little bit above it? That's going to be 0.202. And when we typed in decimals, I don't remember what was it? 0.49, 4.95, 0495, 0495, 0495. You see how that's a little higher than that? And you can tell the red function is a little bit above the blue function. When they're exactly the same at point two, but you get off of point two just a little bit, the red's just barely above the blue on that. So you can tell by the graph. And or just, we could just it's approximately the same as that. I could just write it right here, which came out 4.95049. Right? Yeah, almost. So this is almost the same as this. And there we go. So that's what we're doing on that question.